Hi there and welcome to Lab 5. So in Lab 5 we're going to be looking at a new data set on petrels, white-chinned petrels, which is a seabird. So I've downloaded the Lab 5 Markdown document and we're just going to read through. So we've got bycatch of white-chinned petrels, so those are petrels that are caught while they're trying to fish for other things. Okay, so we've got bottom longliners, tuna longliners, squid trawlers and general fish trawlers. They were caught between 2000 and 2003, and we're going to start by reading the data in. Okay, and what we see is that when we read the data in, we've got a number of variables. We've got an autopsy measure, we've got a year, this is probably some identifier, we've got the month, we've got the longitude and latitude where the bird was caught. We've got the area, which is of class character. So these other ones are numbers. So this is a grouping variable. And then we've got a bunch of measurements. So we've got the Coleman depth and the Coleman width, the bill depth maybe, least depth maybe, nostril length, tarsus length, the right tarsus length, the left tarsus length, the tail length, the right wing length, the left wing length. We've also got the sex, which again is a grouping variable. Okay, so the summary variable, so the summary kind of gives us an idea of the data, and one of the things it tells us is that we've got a bunch of missing values in some of this data. Okay, and so we may want to get rid of the missing values to start with, and that's what the na.omit command does. Okay. So if we run that, we're going to create a new data frame called petrels. So you can see we've got all petrels here with 722 observations. We've got petrels with 659. So the na.omit removes any row in which you have a missing value in na. Okay, na stands for not available. So now when we do the summary, you can see we've got no nas present there anymore. Okay, so now we're going to start doing some exploratory data analysis, looking at this data, and the first thing we're going to do is we're going to look at a table of sex by area using the table function. So the table function operates on a set of data, so we could just do, for example, table petrels $sex would just table up the sex column. Okay, so you can see this data are dominated by male birds, and if you put two variables, then it will table it up by the other variable. So here we've got areas A through F, and we've got female and male. So you can see that in area C there's only 13 birds, and in area F there's only 12 birds total. Okay, and the other thing we notice is that if you just kind of look at the proportion within each column here, you can see that that D and F have a higher proportion of females, relatively speaking, whereas E has the lowest proportion of females, the highest proportion of males. So alternatively, we can do that with a bar chart. So the geom bar does that. What that does is it counts up the number by area, separately by sex, and gives us a bar chart. Okay. So by default, so we've specified the fill as sex, and you can see here that this easily allows us to compare the groups. So we can see that A has the most birds, then B, then E, then D, then C and F have the least birds. And you can also get some feel of the proportion of females and males. So you can see that E has a lower proportion, but it's a little bit harder to tell, isn't it? Because we've got different heights. So there's a couple of things that we can do to tweak this. So if you're interested in proportions, you can say position equals fill, and what that will do is fill up the height of each bar. So it converts the counts to proportions. Okay, and so that allows you to easily compare the proportions. So you can see that E has the highest proportion of males, and D and F have the lowest proportion of males. But what this plot doesn't give you is the counts. Right, you've lost the count, so we can't tell, for example, that D and F actually have very few birds in it. The other one you can do is dodge. So dodge will put them side by side. Okay, so that's the dodge. So again, it's hard to talk about proportions, but easy to talk about counts here. Excuse me. Okay, we could change the y-axis label as well if we want to. So for example, when we do position equals fill, then we could add on labs and say y equals proportion. Okay, that's one way to do that. So using position equals fill allows us to compare proportion across the areas using, but we lose the overall counts. Position equals stack, that's the default. So if you don't specify position, it'll use stack, or position equals dodge allows us to compare counts, but proportions are harder to distinguish. So it depends on what the question that you're interested in, really. And in this case, really, we're after proportion, so I think this one here is probably the best. Let's just actually write those other ones in, just so that we've got them for later. All right, so we'll put no position, which is position equals stack, and position equals dodge as well. And of course we won't need to change the label on that one. So we have all three there. Whoops, I made a mistake there. Oh, I've got a plus. Okay, so when we run it, we'll have the three plots that we can then flick between. Okay. Right. So now we're going to have a look at how the size differs between the sexes in the regions. Okay, so we're going to be using the right wing length as a proxy for size. We could use the left one as well. So we're going to add a new code chunk, and we're going to perhaps use a histogram. So there's a histogram of the right wing. Maybe we'll specify the number of bins a little bit less. There we go. Okay, so you can see that it's mostly symmetric, really. There's a couple of observations that are quite low down here, outlying observations, but mostly symmetric, centered at about 390 or so. We could try and color it by sex, or fill by sex, and we get this. Now the problem with this is stacking again. Right, so you'll notice that the overall shape there is the same as when I didn't have it by sex, right? Exactly the same shape, but what I've done is I've filled in underneath colouring by sex. So it's hard to compare the distributions of the females versus the males, because the males are the ones that start on the baseline. The females start where the males left off. So it's hard to compare the shapes here. So you could add position equals dodge, which would put them next to each other, so you can sort of compare them. It's not kind of ideal. We'll look at another way to do this a little bit in a little bit, using faceting. We could also, of course, use a density. Right, we don't need the bins, we don't need the position. Right, that would put them next to each other so that we can compare, and if we put a bit of transparency on, we can see through. So you can see here that the shapes are kind of the same, aren't they? But the female one is perhaps shifted a little bit towards the lower values, towards the left. So maybe females have a slightly lower right wing length, so they're slightly smaller compared to the males. And of course we could also do a box plot. Okay, and again you see that same result where where things are just shifted a little bit. Notice I don't really need the alpha here, but what it's doing is it's making the box slightly transparent, isn't it? If I get rid of the alpha from that, because we don't have to see through things, they'll just be darker. Okay, so these are all three plots there. Okay, so our overall conclusion is that the distributions of right wing lengths within male and female birds are similar, mostly symmetric, around about 385 to 390 millimeters, I guess that is. However, female birds are on average a bit smaller than males, but not by much. Maybe 3 millimeters or so. Right, so not large differences here. Okay, so now we could have a look at different areas. We could do the same thing as we did before. So just basically take that same code we had and swap out area for sex for area, and let's see how we go. Okay, so this is where things start getting messy for histogram, right? It's really, really hard to compare these distributions because it's kind of hard to see, particularly when the numbers are different. So the F group is, really hard to see here, and so on, right? So there does seem to be some evidence that maybe the blue group, area E, is higher, and that maybe area B is lower. But it's kind of hard to tell. Much easier with the densities, but still it's a bit of a mess, isn't it? Okay, so area E does seem to be a lot higher, and a lot of the other ones seem to be kind of a little bit more similar. The box plots are much easier to determine, and I think with this many, it's almost better to switch the role of the axes. So let's switch them round. So let's make, let's put area on the x-axis and right wing length on the y-axis, which will switch them around, and that's kind of fits the a landscape plot a little bit better. And of course, the box plot here, this is really showing off where a box plot is awesome, right? A box plot is really great when you have lots of groups to compare, because you can easily compare each box with each other, right? So you can see that the E group here is the biggest, then the A, then all of the others are about the same. Okay, so okay, but we might be able to use faceting for this. So let's grab our histogram and let's try to add a facet. So instead of position dodge, what I'm going to do is I'm going to add in facet wrap vars area. So what this does is break the data up by area. Okay, so the vars function is similar to the AES. It's kind of defining the mapping that you're using for the variables that you're going to split by. And so here we're splitting the data up by area, and then we're doing a histogram within each one with the scales all fixed to be exactly the same, so that we can easily compare. So you can see here that E is clearly the highest, clearly higher than B. A little bit hard to compare, I guess, because we're comparing across instead of up and down. Like you can compare the B and E really easily. A little bit harder to compare some of the other ones. And of course the colour here doesn't really matter anymore, does it? We could actually get rid of the fill equals area if we wanted to, because we don't need it, right? We've got the different areas are within each group, but nonetheless the colours look kind of cool anyway. But we could specify a single one if we want. Right, whatever we want. And a density would work the same. Okay, we don't need the bins. Let's just repeat that code so we've got a record of it for later. Don't need the bins. Okay, so you can do densities as well. Okay, so the overall thing we notice is that area E has the larger birds, right? And so there's a question of why does area E have larger birds? So let's just go back through and kind of think about what we've done so far. So what we found is that area E has the larger birds, but we also found that males were bigger than females. And also that area E had a higher proportion of males than females. So what might be going on here is area E has a higher proportion of males. Male birds are bigger than female birds. So when you look at area E and don't distinguish by sex, what you're seeing is many male birds. And the male birds are bigger, and so that may be what is pushing area E up. Okay, so it's plausible that area E has larger birds due to it having a higher proportion of male birds, which we know are bigger, i.e. the difference we see between the areas might just be due to the proportion of male birds changing. Okay. So an easy way to check this is to incorporate sex as well, right? So let's grab our box plot that we did before, and we'll put sex on it as well. So notice on this box plot, the colour is actually not actually important here, right? I mean, it looks pretty, but you know, we can distinguish them because we know what the area is along the x-axis anyway. So we can get rid of the fill by area and would still have the same conclusion as to, you know, which groups are bigger. And that then gives us the opportunity to use the fill, or the colour perhaps, as an additional variable, right? So instead of filling by area, we could fill by sex, right? And now we can perhaps answer whether this conclusion that we found here, this plausible explanation for area E being bigger, we could check this because now we've actually split everything by sex, haven't we? So you can see here that if you just look at the red ones, which are the females, you can see that area E is still bigger, but only maybe a little bit bigger than area A. And if you look at the males, then area E is also biggest. So looking just at the females, area E are bigger, and just at the males, area E are bigger. So it can't be due to the different proportions of males and females, right? There must be something intrinsic about the birds in area E that are making them bigger. Okay. Now there's a couple of other ways we can do the same plot. So we could use faceting. So it's kind of similar to position dodge this, right? Where we've got the two distributions, we've got the two sets of box plots, and they've just been shifted next to each other. But we could instead use faceting. So we could wrap by sex. Okay, and there they are side by side. Okay, so you can see here that the male ones tend to be higher than the female ones within each group, and within the females and within the males, the area E are the larger birds. Okay, and you can play around with this, so you could put them on top of each other, for example, by specifying number of rows is 2. Okay, so that allows you to compare the patterns, but you can't you can't compare the relative height of male versus female. So 2 columns allows you to compare the relative height of male versus female, and you could also reverse the faceting, right? So you could, another plot you might do is reverse the roles of area and sex. So you could do X is sex, fill is area, and wrap by area. Okay, that's another way around you could do it. Okay, so this allows you to compare the males versus females within each area, but it's a little bit harder to see how each area changes. Right, so depending on the question you want to answer, different plots will give you different things. Right, maybe actually filling it by sex might be better here. Do we think? Yeah, I don't really know. But this allows you to compare, like within C, what's the difference between the sexes? Within F, what's the difference between the sexes? But it's harder to see the differences between A and B and C, and D and E, and so on. So if your primary thing is, are the areas different, then I think the previous graph is probably better. Okay, because you can see the pattern of the areas within the males and the females. Okay, so our conclusion is that the pattern of which area is bigger is pretty similar for female birds and male birds. Area E is largest in each case. So the changing proportion of females and males isn't what is explaining the area E being larger, as both female and male birds in area E are larger than their counterparts in other areas. Okay, so now we're going to go on to exercise 2, which is on statistical inference. So I'm just going to add a heading here. Remember, headings are done with the little hash. So this is a level 2 heading. Okay. And now we're going to compute confidence intervals. So you remember, confidence intervals are what we allow us to go from our sample back to the population. So here we have a sample. It's perhaps not a random sample because it's bycatch, right? So it's a convenient sample. It's the birds that happen to be caught while the trawlers were trying to catch fish. So it's not going to be necessarily representative of the population unless the population are focused in the areas in which these trawlers are doing their thing. Right, so what is this code doing? So this code is, so the goal here is compare male and female birds. The differences that we saw on our graphs likely also to exist in the population. Right, so remember, statistical inference is all about taking what we see in a sample back to the population. Okay, right, so this code is pulling out the males and the females. So you can see we've got 529 males, 130 females. That adds up to the 659 total. And now we're going to look at a confidence interval for the average right wing length in males using t.test. So the same as what we looked at in lecture 4. So you remember the key. So here's the mean of the males, 388. Let's check if that makes sense given our graphs. So here's the males here, 388, so this is 380, that's 390, so 388 is somewhere in the middle there. That looks about right. Remember, this is the median, not the mean, but because it's symmetric, the mean is probably fairly close to the median anyway. So that's our best guess at what the mean is, and then this is our confidence interval, right? So we could say we're 95% confident that the average right wing length of male birds in the population is between 387.6 and 389.2. So that's actually a very precise range, isn't it? It's only a couple of millimeters not even 2 millimeters, 1.5 millimeters of range. So we've got a very, very precise estimate for the male birds, and we could do the same for the female birds. All right, so here's the female birds. For females, we're 95% confident the average right wing length is between 383.5 and 387. Okay, so what we notice is we have evidence of a difference, don't we? As these confidence intervals don't overlap. Right, so our low end for our males is 387.6 and our high end for the females is 387. So the intervals don't overlap, so we have evidence of a difference there. Okay. So male petrels are on average larger than female petrels in the population. Right. Right. So what about area? So we could repeat the same process for area instead, right? So we could do this same process. Let's copy and paste that for area. This time we're going area is A, area is E, and so on, right? You could do it. You could do it for a whole bunch of different things. Let's just do area A and area E, but you could do it for all of them, right? There's area A, area E. These names that I'm making up here are just whatever you like. You can call it whatever you like. Just make sure that you remember to use the right thing, right? So there's area A. That's the area A birds. If I click on that, have a look at area. Where's area? There, they're just all area A, right? Area E birds will just be all area E, right? So we've got 259 and 120. That's the same as what we had in our table way back up here. So in area A, we've got 52 plus 207. That's 259. And in area E, we have 120. That seems right. And so we could test A and E. Okay, so we're 95% confident that the mean right wing length of birds in area A is between 388.6 and 390.9. And in area E are between 392.2 and 395. So again, these intervals don't overlap. Right, if you look at the high end for this is 391, near enough. Low end for this is 392, so they don't overlap. So area E birds are larger on average than area A birds in the population. So not just in our sample, but likely in our population as well. Now here we've just compared area A and E, but there's lots of other comparisons we could do, right? We could do area A versus area B. We could do A versus C, A versus D, A versus E, which is the one we've done, A versus F, B versus C, B versus D, B versus E, and so on, right? There's a whole heap of pairwise comparisons here that we could do. I think there's 15 of them. And so that's quite complicated. We'd have to repeat this code a bunch of times. So there's a little bit of code that I've popped in the lab sheet that does it all at once, which is this magic code here. So I just want to walk you through what this does. You're not expected to be able to reproduce this, although of course you can copy and paste it if you want. So there's kind of three things that have been done here. So the first thing, the t-apply, what that's doing is it's taking the right wing length and it's breaking it up by area, right? So subsetting by area, and then it's running t.test on each one. Okay. So essentially, this is doing this step here. So we're doing the subset and the t.test. Okay, so let's just run that and see what happens. Okay, we've got a new variable t-tests, and if we have a look at t-tests, it's this list thing, bunch of lists, and if you have a look inside each list item, then you get the information from the t-test, right? So here's the, so we'll probably have our estimate of the mean, and we'll have a confidence interval and stuff there as well. The second command is then tidying it up with the Broom library. Now some of you on your laptops may not have Broom installed, so you might have to install it via packages, install, and type in Broom. Okay, and then click install. You may also need dplyr, which is this next one. Okay, so when I run that, I get a tidy list. So if I have a look at that, then each one is then a little bit tidier than I had before. And then the last one is what I bind them together. So I combine them into a single data frame. Okay, so you don't really need to know exactly what the code's doing. All you need to know is how to kind of interpret it, right? So it's just a way to run the t.test on each of the areas individually, just like we did above, but summarize them in a single row instead of all this other output. And what of course we have is the confidence low and the confidence high. This is our confidence interval here. And so here's our area A1, the same numbers as we had above. So there's 388.6, 390.9, same numbers. And there's the area E, the same as we had before. But now we can easily compare across groups, right? So you can easily see that the low end for the area E group, 392.2, is higher than the high end for all of the other groups, right? The nearest one is area C. Okay, so area E birds are larger in the population. Another way to do this is you can actually, you could plot this now that we've got it in there. So if we take the combined data frame, then we could use geom_point, where X is the area, Y is the estimate, right? That'll be our mean. So these are the means within each group. So you can see area E has the biggest mean. And then we could add the error bars as well. So you could go geom, is it line range, I think. Let me just look up the help for that and see how that works. Right, line range. So we need, what variables do we need? We need the X or Y, Y min and Y max. Okay, so we want X as area. Y min is going to be our conf low. Is that what it was called? Yes. And our Y max is going to be conf high. So there you go. There's the confidence intervals. Labs Y equals mean right wing length. Okay, so you can see here the area E is easily bigger than the other areas. So it seems as though area E is like the biggest. Area A is then probably next largest, and all of the others are kind of similar. Notice there's a lot of uncertainty about area C and area F, and that's just because we don't have many observations there, right? Area F only had 12 birds in it, so we can't be very confident based on that, right? You remember that the length of the confidence interval will have something to do with essentially the standard error, right? The standard deviation of the sample mean. The standard deviation of the sample mean had to do with the sample size, right? So as you increase the sample size, you reduce the length of your confidence interval, right? So these confidence intervals for A, B, and E are small because we've got lots of birds in those areas. Okay, so Right. So that's how you can compare across lots and lots of groups. We'll see another way to do this later on with a linear model, but we're just going to go back to the sex ones, and we compared these. When we just have two areas, we could compare them with separate confidence intervals for each area and then see whether they overlap. But the other way to do that, because we've just got two, is we could look at the difference between males and females. Okay, so alright, so that's what this other form of the T-dot test does. Right, this is called the formula form, and how to read it is right wing length, the little tilde, which is top left of your keyboard, just below the escape key, means in terms of, so right wing length in terms of sex, and we're taking the right wing length and the sex from the petrels data. So when we run that, what we get is this output here, and this is a confidence interval for the difference between them. Average right wing length difference in average right wing length between males and females. So you can see the average in each group. Female 385.3, male 388.4. So the difference, females minus males, will be 385.3 minus 388.4. Let's just work that out. We can use R for that, or a calculator, right? Minus 3.1. Okay, now it's negative because I did females minus males, right? And so I did the first group minus the second group, and females were smaller than males. So when you subtract a larger number from a smaller number, you get a negative, right? So the 3.1 millimeters different. The confidence interval then is a confidence interval for that difference. So it's saying, that's the 3.1 is the number that we got in our sample, right? So that's just the difference between the sample mean of each group. And so now that difference is going to follow a central limit theorem, just like the mean follows a central limit theorem. And so we're going to be able to add the standard error around that estimate in order to get a confidence interval. So that's what the confidence interval does. So we can be 95% confident that the difference between female and male birds lies between so difference in average right wing length between female and male birds in the population lies between minus 5.1 millimeters and minus 1.2 millimeters, right? So males are between 1.2 and 5.1 larger than females, right? Females minus males is a negative number in both cases. So in both cases, at both extremes, males are bigger. So our conclusion is we'd be at least 95% confident that males are larger than females. So okay, we'll look at formalizing this idea of can we say that males are larger than females, and can we put sort of a number on it that allows us to express how much evidence we might have for that when we look at hypothesis tests. So that's where the p-value comes in. Okay, so all I'm using here is the confidence interval and the values from the female and male. Really all I'm really using is the confidence interval. So what I'm looking for is, are the signs here, the negatives and positives, are they the same, right? So if I've got two negatives, right, which means that in both extremes, females are smaller than males, right? The first group is smaller than the second group. If I had two positives, so if I reverse the roles of male and female, swap them around, then I would get the same confidence interval, but they'd be two positive numbers, so I'd have 1.2 to 5.1, right? They'd both be positive numbers. Then again, I'd be concluding that males are bigger than females. The difference is when if I have a negative and a positive. So if I have a negative and a positive, then that's saying that I'm 95% confident that females would be less than males, or females are bigger than males. So they could be the same, right? So what I'm looking for, when I'm looking for is there a difference between two groups, is I'm looking for whether the difference, the confidence interval for the difference, contains 0 or not. So is 0 a number that is consistent with the data that we have? Okay, or is our data consistent with 0, I suppose is a better way of putting it. That's what I'm looking for. So for example, maybe if we try and do another one, let's see if we can see if there's a difference between between B and C. Looking at the graph, there shouldn't be, right? So let's have a look. So let's have a look at an example of no difference. Let's grab so area B and C is we're going to take the petrels data and subset it such that the area is equal to B. Okay. Right, so area BC. Okay, if you look at the area variable, we've got B's and C's. There's some C's there. Okay, so the in here means is area in the C is putting together the B and the C as a single unit. So this is saying is area in B or C. And then once we've got that, we can then do our t-dot test on the difference. So we could say right wing length in terms of area from the area BC data. This won't be doable if we use the original petrels data because area has 6 groups, right? So this formula set up for the t-dot test only works if you've got 2 groups. Right, so when we do this, it says, well, the area in group B is 383.9, the area in group C is 384.3, right? The difference between them is just a little bit negative, like minus 0.5. And we're 95% confident that difference is between minus 7.5 and 6.6, right? So area B is either smaller by area A by 7.5 millimeters, or area B is larger than area A by up to. Okay, they could be the same. So a difference of 0, i.e. B and C being the same, is inside our confidence interval. So our data are consistent with a difference of 0 between B and C, i.e. consistent with them being the same. Okay. So what you're looking for is 0 in the interval, right? Up in this case, it wasn't, right? They're both negative, so 0 is outside that interval. It's to the right of the interval. Here, 0 is inside the interval, so we're concluding that they could be the same, right? Our data are consistent with a difference of 0. That's it. So we'll look at this, kind of formalize this idea of testing specific things. So is there a difference in lecture 5? Let's knit that document just to check it's all going to run. There we go. Okay, let's check we've got all our plots there. Yep, that's looking good. Okay.